Hi, everyone. I'm really happy to have the first talk this semester in spring 2020 with Vijay Subramanian. And I have a guest appearance here from Sid Jaggi from Hong Kong. He's visiting Rutgers. And Vijay is going to talk today about personalized PageRank dimensionality and algorithmic implications.
Thanks a lot, Salim. And yeah, my first time doing an online version, so it'll be good. I'm going to see how it works. Let me share my screen and get going. So can you see everything fine?
Yeah.
All right, great. Okay, so this talk is titled Personalized PageRank Dimensionality and Algorithmic Applications. This is actually joint work with my now just recently graduated student, Dr. Daniel Vial, who's doing a postdoc now at UT Austin. He just started this week. So let me give some sort of this. I mean, this work has appeared now in ICM Sigmetrics last year, and I really am very fond of this. So please stop me if you have any questions, but I try to give you a flavor of the results and how things work. So I'll start with some motivation. So the graphs arise in many domains and are used to understand processes, behaviors, and vulnerabilities. I mean, some examples are social networks, the internet, the power grid, and so on and so forth. They've been very successful. And if I may reuse a quote by John Kleinberg from his Allerton 2014 plenary, he basically says, in the battle of ideas for metaphors, for explaining all of these things, graphs are doing pretty well. So this is the context in which this work is framed. So the questions of interest in this talk are, which nodes, you're given a graph, which nodes are most important, influential, and both in sort of a global sense and a local sense. And when I'm looking at the local sense, I'm looking at questions of the kind, which nodes are similar or relevant to a given node? And so these two questions have been looked at for a while. It's not like we're looking at new. And in fact, there has been a metric that's been in place for a long time to understand this, and this is the personalized PageRank metric. So some of you may be familiar with PageRank, but not personalized PageRank. So part of what I will do in the beginning is sort of introduce what that is. So here is where I'm going into that. I mean, I'll have a sort of pictorial representation and then also give you a more formal one in terms of the process. So you're given a directed graph, G, with V edges and, V vertices or nodes and E edges. And I'm going to pick a node, say V. I'm going to call that a distinguished node. And I have a number alpha which lies between 0 and 1. Okay? And so this is why if you look at the picture below, I'm drawing this graph with V as being highlighted, and everything is sort of looked at from the viewpoint of V. Okay? So I'm going to define a Markov chain on this graph, which the state space of the Markov chain is the nodes of this graph. And the Markov chain works as follows. If you're in a node at time tx, v of t, v actually signifies something important about this Markov chain, which I'll explain very soon. What you do is you toss a coin. It's a biased coin. With probability 1 minus alpha, you do something. With probability alpha, you do something else. So with 1 minus alpha, what you do is you look at the outgoing neighbors of this location where you are, and you pick one of them at random and you go out, move in that direction. This is the random walk. Now you may ask what happens if there are no outgoing neighbors, then you just stay there. With the other probability alpha, what happens is that you reset or you jump back to node V and restart this whole process. So this defines a Markov chain, which is sort of parameterized by the node V. I can look at the stationary distribution of this Markov chain, and it's easy to show that it always exists. These Markov chains are what are called Dublin chains, and they are always they are irreducible, aperiodic, so on and so forth. And so I call this stationary distribution the personalized PageRank vector corresponding to node V. And then I'm going to look at all of these vectors with respect to all the nodes in the graph. So I get for node V, I get one thing for pi V. For node U, I get pi U. I stack these up as rows of a matrix, and I call this a matrix pi, capital Pi, the personalized PageRank matrix. This is a row stochastic matrix, and this is the matrix that we are trying to try to study in this work. So Any questions on that? I mean, so what, to put it differently, and this perspective is very valuable, you have the random walk, which is the regular marker process on this graph. And then you have several sort of perturbations of it. And the perturbations correspond to each of the nodes.
Should we worry about the graph is directed?
Process jumping back to node V. And so I have, if there are V nodes, I have V Markov chains, and I'm going to try to understand the stationary distribution of each of those, how they're related. And the backdrop is they all are closely related by this random walk that is underlying it on the graph. Is that clear? So I mean, there are lots of Markov chains. I'm trying to understand the relationship between the stationary distributions.
Can you hear me, Vijay, now?
Yeah, I can hear you. Yeah.
Yeah, I had a question. So is there something that we should worry about, that the graph is directed? Can something go wrong?
So the graph is assumed to be directed. Nothing goes wrong here. So what you look at is, so a way to understand how the stationary distribution always exists is you just look at the nodes that you can reach going out from V using the directions of the edges. And
you suppose you can reach
another node, you'll put value 0, and these nodes will have positive probability. And that's going to be a stationary distribution. Just the connected component means, in terms of going out where you have a path going from V to that node that is sufficient.
Okay, thanks.
But that's a good question. So yeah. So why is this useful? So the general interpretation is, for a node W, if pi V W is large, then W is visited frequently on sort of short walks from V. And that's measured as a measure of the W's importance or relevance to V. Okay. And this sort of notion has been used both for, the regular PageRank and now personalized PageRank. And it's been used for lots of different things. One of the things that it's been used for is actually recommendations. In fact, personalized PageRank is somewhat used for places like LinkedIn and Facebook to recommend new connections. You look at the personalized PageRank from the person's point. If it's high, then you say it must be a friend, because there is some reason why this person has importance or relevance. It's been used for bioinformatics. It's also, in a way, if the personalized PageRank is large, which means that you're in the same community. If it's very small, it's in a different community. It's been used for community detection from that viewpoint, also to understand graph similarities. And there's a vast literature. I'm just giving you a snapshot of things that it's useful for. So going more formally, so I just gave you a pictorial view there. So I have a directed graph. And say I said V edges, and sometimes I can use N as the number. When I'm looking at complexity numbers, I'll say N, V node, sorry. M is the number of edges. So I'm going to, for this discussion, let's assume that every node has at least a single outgoing, out degree is at least 1. And so I take the adjacency matrix, I take the diagonal out degree matrix D, and I then construct this row stochastic matrix P, which is D inverse times A. This is basically the transition kernel of the random walk. So it's going to pick one of the outgoing nodes and then move along those lines. So the personalized PageRank is actually, now there's a more general class of things. I defined it with respect to a node, but you can define it with respect to a distribution on nodes, and I call that distribution sigma. Pi sigma is the personalized PageRank corresponding to distribution sigma, and that is given as the Perron-Frobenius eigenvector of the following non-negative matrix, which is basically 1 minus alpha times the random walk, and alpha times restarting with distribution sigma. So what you do is you toss this bias coin wherever you are. If you with 1 minus alpha, you follow the random walk. With alpha, you just reset. And when you reset, you sample nodes on the graph with probability given, distribution given by sigma. And this, if you rewrite everything, this is the transition kernel that you get. So we'd already seen this. If sigma was a point mass on node V or node S, then you get this personalized PageRank with respect to S, pi S, or pi V. The regular PageRank that you're used to is basically sigma is now the uniform distribution on all the nodes. And so basically when you reset, you go to a completely different node of the graph. I mean, you should pick a node at random and go there. And so the interpretation in some sense of the way these things have been used is that the global page rank, which is what was initially proposed, has the following viewpoint. You are on a web page, you look at any of the links of the web page and you follow that for a while. So the links are the web page points to, so this is the outgoing links. And then at some point in time, you follow 10 links, maybe you're more, today you're very patient, you follow 20 links, and then you get bored. You say, hey, I'm going to restart. Right? On the population level, it's fine to assume that you start uniformly across all nodes of the internet here. But at a personal level, you may have certain favorites. You may decide that, hey, I am very personal, self-centered, so I always start on my web page and then march out. Some others may say my department or I don't know, CNN, Google, whatever. But you have a preference or a different distribution on the network, on the nodes of the graph than uniform. And so you start with sigma. And what the search results would, if you use a personalized page rank, then the search results would be tailored to your preferences. And that's the way they want to use this thing, for example. All right. So allied with the whole topic of understanding this personalized page rank measure, which is a centrality measure, there's also been a lot of work on the computation of it, which I think is also a reason why this problem has been very interesting and had lots of attention of lots of people, because there are different methods to approach the problem. One is to take the linear algebraic method. I have a non-negative matrix, so the Perron-Frobenius theorem holds. It's actually, as I said, it's basically irreducible, aperiodic, everything. So I can just take the power method and variance of that. So if I do it for every node, basically this will be like order n squared. I just use a naive power method. And this can be very high in terms of computation. So what I think from numbers that I've seen, I've heard, I don't know what the current numbers are. When Google runs it, it takes about at least 2-3 weeks to a month, maybe a couple of months to do whenever they redo the whole page rank calculations for the whole internet. Now, obviously, this is not that acceptable. So what people have looked at actually in the linear algebraic method, there's recent work coming out of computer science, theoretical computer science. It's called the directed Laplacian variance. This is by Gary Miller, Daniel Spielman, Xinghua Teng, Richard Peng, etc. And there you can do almost linear time, and I mean almost linear time is linear number of the edges. Okay. This is far from implementable, but it says that there are algorithms that exist from that scale. Okay. The other way that people have looked at is this probabilistic method. Now P, as I said, is basically the transition kernel of a simple random walk. And these particular PPR Markov chains, which have this reset, have a very nice property, which I'll talk about very soon. You can get what is called perfect sampling from them. And so you can use Monte Carlo algorithms like random walks basically to estimate this personalized page rank. And if done well, so for example, for the global page rank, is work by Avrachenko, others, and Sarma, etc., where you can get it in sort of order n log n complexity as opposed to O(n) squared. I'm not telling you what the error criteria are, but that'll come through very soon when I talk about more the rest of it. The third way that people have looked at is to look at this. So you're computing a stationary distribution, and that you can take it in terms of a sort of a dynamic programming viewpoint. And so it is written basically, it's like policy evaluation and say Markov decision processes. In the sense you're not doing policy iteration, but you have one policy that is fixed and you want to find out the value of the policy. And then that eigenvector computation or it's called the Poisson equation can be written as the Bellman equation basically. And then you can use that value iteration ideas to compute it. And this is related to the power method, except it doesn't always take uniform length paths. It takes different length paths it assesses value based on the actual probability that you get. And this effort was pioneered by Anderson, Chung, Lang, and then Anderson et al. These two references will actually come back later on in the talk. So if I don't give you any details now, it's going to come much later. And then people have actually built on these things to come up with hybrid schemes. Some of them use Monte Carlo and the variational method. In fact, there's a very nice paper by Peter Lofgren, Sid Banerjee, and Ashish Goyal, where they have this pi matrix. You want to estimate a single entry, and you can actually get quite a bit of savings by doing if you use the Monte Carlo in one way, so a forward Monte Carlo and a backward thing using the variational method. So this is sort of.
I have a small question again, Vijay.
Sure.
So because you gave the Google example, so suppose the graph changes a little bit, can I use the previous computation to not
Yes,
go?
I think there is some. Yes, there is some smoothness too, but in our case, we assume that the graph is fixed. And so there is some work now using how the random walks will move how the stationary distribution changes as the graph changes. And you can use that to sort of rely and use that to speed up your computation.
Do you know if
I'm not 100% sure what the complexity results are. So yeah.
Thanks.
So coming back again, as I said, I was mentioning that these type of chains are special. These are actually what's called a Dublin chain. It's well known in sort of the probability literature. It's been there for a very long time. It's actually initially when they looked at stability of Markov chains, this is one broad class of Markov chains where you can get stability, that's positive recurrence. In fact, there's a beautiful paper by Atreya and Stenflo where they sort of show that these are about the only chains where you can get these what's called perfect sampling. And what do I mean by perfect sampling is I can sample from the stationary distribution exactly. So most Markov chains, you have to run it for a while, you think it has mixed, and then you get a sample which is close to the stationary distribution. Here, there is an exact point of time when you can get samples from the stationary distribution. And what is that? So like I said, I have this reset. So I'm tossing this a bias coin, 1 minus alpha type thing, and every time I get an alpha, I look at it as a reset. So I can think of that as a geometric length random walk, geometric distribution, the length is parameterized by alpha. So at the end of that, I reset. I start at node S. Right? I look at the node where I am when I decided to reset. That node, the probability that the random walk is resetting there is exactly the stationary distribution of that Markov chain. So the way to sample from this, you basically just take a geometric random walk, look just where you're resetting, look at the node where you are, and you do multiple, you get an unbiased sample from the stationary distribution. You keep repeating it, you can do any estimate that you want, so on and so forth. And using this idea, you can actually then sort of easily understand that you can also do this using linear algebra, that it's sufficient that in the personalized PageRank domain, the primitives are not, so I said you can have any distribution on the nodes. If I know the personalized PageRank corresponding to every node, this pi s, and I know the distribution that you're using, sigma s, if I just average these pi s's with respect to sigma, I will get the personalized PageRank with respect to sigma. So this relationship that is equation 3 here is a core. So in some sense, the primitives are that PPR matrix that I had, the big pi. If I estimate all those rows, then I can give you any personalized PageRank that I want. Okay, so this is where we are sort of going in some sense. I want to estimate that particular matrix, big core matrix pi. There's also renewal reward interpretation. I said basically it's a number of visits and on a geometric length random walk because you get renewals. And that can be used to get better, more accurate estimates of this. All right, so let's now go to the basic question that I'm going to ask. And this is going to go, the talk will have two parts. One is sort of the dimensionality part, and then sort of looking at algorithms in some ways. Okay. So if I look at this matrix, I want to estimate this matrix pi, where remember each row corresponds to the personalized PageRank that I'm resetting to a specific node. And I'm running this over all the nodes, so I get this whole n by n matrix. What you can easily show using the Perron-Frobenius theorem, there are other ways as well, that the rank of this pi is exactly n. So it's a full rank matrix. So it's all it's row stochastic, so it's probability vectors, but it is full rank. So this is and so in some sense, it looks like if you have to estimate it, you may have to basically estimate each of them separately. But if you think about it a little bit, personalized PageRank actually exhibits a transitive structure. So suppose I'm given 3 nodes, V1, V2, and V3. If pi V2 with respect to V1 is large and pi V3 with respect to V2 is large, that is basically V2 is important to node V1, V3 is important to node V2, then you sort of can argue that V3 will be important with respect to V1 as well. In some sense, a friend of my friend is a friend. And this type of idea is usually used to predict friends or new connections in Facebook and LinkedIn and various things. This somewhat suggests that pi should have an effective, effective dimension must be small. Another way, this is the first one is much more an intuitive reason why you think there should be a small dimension. The second one is sort of a more this brute force calculation. I don't think this is the most relevant intuition. So we know that this, the graphs, if they're sparse, they're roughly, very loosely put, they're sort of linear in dimension. But pi square, as I said, it's full rank. I know it sums to 1. So in some sense, I have like order n squared dimensional in terms of the numbers that I'm representing it, and they seem like all of them are important. But if the graph is somewhat sparse, I feel there should be some relationships and things should collapse, and how should that actually proceed? This is another way of thinking about this problem. So now that I've given you all this introduction, so something I know people are not familiar with personalized PageRank. So what we're going to do actually is basically is first sort of say, how do you quantify this effective dimension of pi? What makes sense? I know if I go with the regular like rank definition, it's fully n. Then can I bound this measure of dimensionality and show under certain for certain graph families, can I show it's going to be small? What do I mean by small? It will all come through very soon. And if this bound is small, can we leverage it algorithmically to sort of estimate this whole matrix pi? This is basically the extent of the talk. I know I have 30 minutes to go, but I will get through. And it's all right if I don't finish it. It's no problem. Yeah. So what we step back a little bit and ask this question. I have a full rank matrix. I know it has some effective dimension that is small. So the kind of question you would, the exercise you would do is, hey, can I come up with, so you give me some error criterion, say that I want to give you an estimate pi hat. And I say that I give you an epsilon error and I give you some matrix norm. I say that the error made by this estimate, so pi minus pi hat in this matrix norm should be less than epsilon. But so I'm looking at all of these estimates that I can provide, and I want to choose the one that has the smallest rank. And if this is small, then I would sort of argue that pi is low dimensional in some sense. So it's very close to a low dimensional matrix, and so things are fine. This is the viewpoint you want to think about. And so this can also be viewed as the dual of the low rank approximation, where you basically fix a rank for the estimate, say it's less than or equal to k, and then you find the lowest your error can be. And these type of problems have been studied quite a bit, except they're always used with one of two norms. One is either the Frobenius norm or the operator norm, in which case we do know what to do here. You just take SVD of pi, and then you just take, if you're doing the dual one, you just take the top k. Or if you're taking the first problem, you'd go up to the fact that the error, the singular values are less, some of them is less than or equal to epsilon. And this is the well-known, this I'm sure is done in many graduate courses on, in machine learning. But think about what we want to do here. So this just running this is not going to be good. Why? Because I'm trying to estimate a row stochastic matrix. So I want non-negative entries. I would be happier if you gave me a pi hat which is closer to a stochastic matrix. Right? So in some sense, but with the operator norm or Frobenius norm type things, I may not be guaranteed. I may get some negative entries, may get a whole bunch of things, especially for numbers when the numbers are small. So I would like to get something that is non-negative, and preferably one that is almost very close to a row stochastic matrix. That's going to be the goal in some sense. That would be a good estimate. I don't have that criterion put in here, but that's what I would like. Right? So is that clear, the objective in some sense? Yeah.
Yes, Vijay, one question is, so could you do the same thing, but like solve the same optimization, but look at all stochastic matrices, like add constraints? Because if you want it to be stochastic.
Yeah, you could add constraints, and I think that would be, it's a convex constraint, and I think that may be one way to do it. But we also want to get good algorithms, and so there'll be a natural way that will come out. I will explain that. And this viewpoint.
And for you, how do you measure goodness of the algorithm?
Yes, I'm going to come to that very soon.
Okay.
Yeah, you could do that too. I think that's a good suggestion, but I don't know how good it will be algorithmically. Right? So what we decided is the right thing to do is, remember we have probability vectors. So I'm going to gauge the goodness in terms of the L1 norm, which is basically, think of it as total variation. L1 norm and total variation are related by a factor of half. So I'm going to compare the error made there in terms of L1 norm, and then I'm going to take the max over all the rows. So this is the matrix infinity norm, as people know. So I want to do the same exercise, this minimum rank, this low rank approximation, or find the effective dimension in a non-traditional norm, which is the matrix infinity norm. Okay. And I don't know how to solve this problem. Maybe someone else knows. Even I think this is probably a non-convex problem. I haven't quite, and maybe it's NP hard as well. I have no idea. Okay, so how would you think about this problem, and why is it sort of useful? Let's look. So since we don't know how to solve it exactly, can we bound it? And can that bound be used algorithmically? This is the next sort of way we're going to go. So let's, actually, it's better to have this picture as well. I'm going to define a bunch of quantities in this equation 6, but I think it's better to start with this picture. So do a thought experiment. Suppose somebody or a genie picked a set of nodes K, subset, it gave you the personalized PageRank vectors exactly. Right? So this is a thought experiment you're doing. So these are, so I know pi v for, pi k for every k that lies in this capital set K. Okay. Then I ask the question, so these are the blue nodes in this picture, as you see. And I ask the question, let's look at the linear subspace spanned by these vectors. Right? And this is what I'm doing when I take this news and I'm adding all these out. And I say, which of the remaining personalized PageRank vectors are within epsilon, L1 epsilon error of this linear subspace. Okay. And those 10 are, in this example, are the green ones. Okay. So I say that maybe I don't know an algorithm yet, but maybe there's some way I can say if there's close enough in this L1, in the L1 distance to the linear subspace span, then I can estimate them well. And I say that that can be done. We'll come up with an algorithm later on, but conceptually, just assume that is done. Then the ones I cannot, those are the ones that are in red. Those are the ones that are basically in the set, yes, in the big expression which says nu does not belong to K such that this minimum is bigger than epsilon, are the ones that are far away from a linear subspace spanned by the ones that I gave. Right? And so what I will do is I'll go ahead and ask the genie to give me all of those separately. And I say that my dimension is basically how many I had to go and ask the genie for, how many personalized PageRank vectors I had asked the genie for. So this would be the original K plus these other ones that were not close to the linear subspace spanned by the ones in the K. So these Ks we'll think of as hub nodes, in some sense located centrally in the graph. We want to find them out in a natural way. And what we will argue is basically for most non-hubs, the personalized PageRank is close to linear combination. And then the number of non-hubs will also be very small, and the hub nodes will also be very small. And this is what I will use to say the dimensionality is small, and then I'll rely on this insight to come up with the estimation problem. Now, I'm sure Salim will ask this. As of now, I'm saying it's a linear subspace. So the linear subspace obviously means the weights can be positive, negative, anything. It'll turn out that we will, so I won't solve this exactly either. This is also a hard problem. I don't know how to solve this. What I will, and especially it has a combinatorial angle. If I want to minimize the K, minimize this overall, all possible Ks, again, that might be NP hard as well. But I think if you do that, you would get exactly the solve the problem that we were setting out with. But what you'll do instead is say, I will actually come up with a subset that seems reasonable. There's some way to justify it. And for that subset, will turn out these weights, mu's, are going to be actually positive, and they will almost sum to 1. And asymptotically, they'll actually sum to 1. So what we'll, to give you some preview of the results, in some sense, what we're going to show is actually you can pick good hub nodes so that almost every other node, except for these bad ones, the red ones, they'll actually lie within a convex hull of the hub. So you are going to get this thing, you will get a matrix which is very close to a row stochastic matrix. So at this point, it's actually good to, yeah. Yeah. So there's some discussion that is needed here as well. So I can do the following for this problem. I can think of what I'm doing. This exercise as follows. I have these K nodes. Basically, I'm collecting these, all the ones that are the hub nodes and the ones I went out and asked for. I collect them on one side. I create that as a matrix H. And then I have these weights, which will be the matrix W. These are both non-negative matrices. And the product of this matrix is very close, will be my estimate. And this will be very close to pi. So effectively, what we'll be doing is a non-negative matrix factorization of pi without ever having a whole pi. And I mean, I've never estimated the whole pi, but I'll do an online sort of, not online, I mean, in the sense of I will generate the H and W as a part of the algorithm. And what we want to know is what are the dimensions. I know that H is basically some n times K, and W will be K times N. What is this K that I get at? And can this factorization be done fast? This is another way of thinking of what we are thinking, the question that we're posing. Is that sort of clear as well?
Yes, yes.
All right, great. And what we'd actually like to do is identify these hub nodes easily too. And sort of the intuition is going to be, can we take nodes that will be visited first by random walks on the web?
So Vijay, these hub nodes, like for example, you know more than I do in these things. Like, I mean, for me, like using current names, like these are the influencers and the social networks, and
you could think of it that way. I haven't thought of it in terms of influencers, but in terms of where, if you look at the random walk on the graph,
yeah,
where it reaches first, I think there's some way of using that as a guide. And I'll tell you more precisely where that comes from. Yeah.
So for example, how bad is if I pick the nodes with the highest degree? Is this a bad
So the question is highest in degree or highest out degree?
Ah, okay.
It's a directed graph.
Okay.
And there will be some reasoning why one is better than the other. We'll come at that very soon. All right. So I defined something that I wanted to do, but it's, again, something that is extremely challenging. I cannot do it because it's highly dependent on the local graph structure. It's hard to bond in general. So what we do next as we modify the problem, well, actually, no, we decide to do here in terms of setting worst case, we'll take an average case analysis of this problem. So I'm actually going to generate graphs from using a random model and then argue for that particular random model. I prove a concentration result, which basically says for this graph, set of graphs, family of graphs, I basically have this dimension being less than something. This is the kind of flavor of results that we're doing. So we analyze this for what's called the directed configuration model, because they have a nice local structure. They're basically, you can couple it to a tree, at least in our case, and you can, or a branching process. And we use that coupling to do most of our analysis. And just a sort of a meta point, I think I've seen other works. I think there's Christina Lee has some work on a completely different plane, where their error criteria is very similar. It's L infinity or L1 type errors. And there too, it's typically, it seems to be in terms of methodology easier to run a process on a tree and then couple things in that manner. This is very different from the random matrix type analysis. And in some sense, these metrics, these norms don't seem to be as interesting to that community, but perhaps based on works, the building body of works, maybe there is some relevance in that as well. So just to give you a quick thing about the directed configuration model construction, the way I'm going to do it is you realize a degree sequence, D out and D in for every node. And this degree sequence will converge to something or the distribution that I'm interested in. What I'm going to do is take, so like a picture here, V1, it has D in is 2 and D out is 2. So I put half edges corresponding to those on each of these nodes. And then what I do is I just basically randomly pair half edges. You could do it by taking a matching. You pair the incoming and the outgoing half edges. But you could also do it in sort of a breadth first search, and this is what we'll do. Both are equivalent, and part of the nice thing with the breadth first search is that allows you to couple an algorithm on it and analyze the algorithm. This is what we will do to find what our dimensionality meant. Okay. You would have noticed, as I've shown here, you can get you get a multi-graph in general. You can get multiple edges. You can get self loops. There are conditions on the degree sequence, some moment conditions under which you'll get a simple graph will be formed with finite probability as n goes to infinity. And then any results that you prove, you can just condition on that. These are all high probability results, so we condition on those, that subset you find.
Do you care about it being connected, or that's not, you don't worry about this?
You don't worry about it.
Okay.
And remember again, so the way my personalized PageRank is structured, basically, I only interested in the connected component of a node that is going all marching out from that node, and the mass will only be non-zero on that.
Okay.
All right, so there is another variable which interestingly has not been looked at so much in the literature, but now there's actually more related work on this, is this reset probability, alpha. And this actually impacts the dimensionality quite a bit. In fact, there is most of the result I'm going to present is basically a phase transition as this alpha changes. And why do you think it might? So let me give you some intuition. So if alpha is 0 or very close to 0, which means you're going to take a very long, basically you mostly follow the random walk. And then after a very long time, you take a reset. And now what will happen here is basically the random walk will mix by the time you start to reset. And so all of these pi v vectors will basically look like the random walk stationary distribution, be very close to that. So in this regime, you would expect that the dimensionality term, there's basically 1, because all of them are so close to the random walk stationary distribution that they're all within L1 of that. So basically that is the effective dimension. On the contrary, suppose you go the other way around and you say alpha is very close to 1. So basically I'm just reset almost immediately as I march out of node V. So the mass will basically get distributed very close to V, and then in sort of a sphere packing type thing. So basically you have vectors which basically are going to put 0 everywhere else and have a small ball around V where the mass is. Then you can sort of see that the dimensionality should be roughly n, order of n at least. Right? So these are two extremes. And what we are interested in is how does this change as you change alpha from this one extreme of alpha being very close to 1, or actually, let's say, more like a constant as n goes to infinity, and alpha goes to 0 as n goes to infinity, but at different speeds. So the kind of question we are asking is, suppose you're given a sequence of graphs from the DCM model, how should alpha n scale with n so that you get something interesting? You don't get these two extremes where the dimensionality is 1 or dimensionality is n. So one example would be, suppose if I take alpha times log n goes to 0, so this will be 1 over log n squared. Then you get the same property that the random walk length is about log n squared, and it turns out for this set of graphs, actually a recent result by Bordenau, Caputo, and Sales, the random walk will mix, actually is fast mixing and mixes in order log n steps. So basically you're going to mix well before the reset happens, and we can then prove that this delta k epsilon is 1 with high probability. And what we'll argue is that the right scaling, where you get non-trivial behavior, is to set alpha to be C over log n. And this will be the right scaling that you get. So you get a phase transition every time. Otherwise, you basically, if it's not C over log n, it will be this dimensionality. So if it's less than that, which means it's going to 0 faster, you'll get 1. If it's greater than that, you'll get you'll get n, and only in this particular regime would you get something that is sublinear. Right? So this is again a preview of the result, but it's tied very closely to the mixing time of the random walk. So a last sort of discussion in some sense before I present the results. Part of it is I'm trying to give you some intuition, because these things are, I mean, the proofs are long, but the intuition actually is helpful. So let's ask another question. Suppose I'm taking it, so I have this PPR vector that I'm coming up with. I have a node V. I walk out for a random walk, of geometric length, and then I reset. Now, if I look at, say, if I look at a neighborhood around this node V, and I look at the stationary distribution, and I want that to be above some constant, fixed constant, say beta, and I want to understand how this neighborhood changes as alpha changes, what type of behavior, then you can actually say the following. If alpha is a constant, as n goes to infinity, then the fixed PPR set, like I said, this beta PPR set around neighborhood around this node is constant size. Again, this would sort of sphere packing-ish ideas will sort of tell you that then the dimensionality must be n, because you have most of the mass is constant around here, and the rest of it is sort of very small, and that's the intuition in some sense. Now, if alpha was C over log n, then this neighborhood, when I fix this PPR value to be beta, increases as n to the gamma for some gamma which is strictly between, say, 0 and 1 as I vary beta. Okay, and so this again tells you why the C over log n is the right sort of regime to consider it. So I have around each node, there's basically a sublinear neighborhood, and these will then start intersecting, and that's when you can think that you would get some sort of a lower dimensionality.
I have a small question. So is it, I don't understand the second point. So why, if it's big theta of 1 over log n, then the ball around V is...
That's a result you can establish. That's one of the things you establish. Yeah.
Okay.
And it turns out this type of scaling is actually related to those who are familiar with all of these things, the Cheeger number or the isoparametric number of the graph family. So these are all, I mean, all of these things sort of fit in a way. So that's another reason why I'm justifying that we will actually consider alpha going to 0, but along the time of C over log n in our analysis. And that's the right regime to look at. The final thing to look at is the question, what would be good hub nodes, right? And this is the question that Salim had also asked. And again, we are going to rely on this random walk as the intuition to pick those, right? So what is interesting in this regime is you have a directed graph, and you have this random walk. You don't know the stationary distribution. If it was undirected, you already know. It's basically just parameterized by, it's basically proportional to the degree of the node, because it's a reversible random walk. If it's undirected, you don't know it. But it's actually what a recent result, again, the work by Bordenov, Caputo, and Sales, they established that it's in some sense, in a very strong sense, close to the normalized in degree distribution. And they actually use that to show this fast mixing. Actually, they show cutoff for these random walks for this graph. And that comes in from the fact that if you start with the in degree distribution, that's a very good approximation to the stationary distribution around. So what we will use in analysis, we'll actually prove whatever we do, we actually prove it. But we use high in degree nodes as the hub nodes, and that will actually be a good choice. In the literature, I haven't mentioned this. When I come to algorithms, I'll mention this thing. There have been other things of using these hubs. And if you take the global PageRank, now remember the global PageRank, if this alpha has this behavior, it's actually going to be close to the random walk distribution. And so it will also be a good candidate to pick the hub nodes. If you look at rank nodes in terms of the global page rank and pick the top K, that will be a good surrogate as well. And the main intuition here is you have to pick something that is very close to the random walk stationary distribution, and that will give you a very good reasoning to pick the hub node. The only thing is if you wanted to page rank, then you're doing a computation. The other high in degree nodes, you're just basically doing one sort and you get it. So that's going to be a saving. Okay, so what's our main result? So I know I'm going a little slower than desired, but that's fine. Please stop me when I, let me know when I have to stop, and I will stop. If some of the intuition gets conveyed, I'm more happy than the other. Okay, so our main result says that for a particular class of random graphs, if I choose as alpha n to be C over log n, then I can show that this dimensionality parameter is bounded by some C n to the C epsilon, where C epsilon is between 0 and 1 with high probability. So I get this concentration type result, which says under this case, it's sublinear. This dimension, effective dimension is sublinear. Just a quick outline of how this proof is happening. I'm not going to go into any detail because the proof is quite long. So I look at of what is of interest is this error that I basically said is.
I have a small question. So
sure.
I'm trying to understand the main result. So we know that the dimension cannot be more than n, right?
Yes.
So it's always sublinear.
Well, it can be n exactly, right? It can be linear.
Oh, it's not big O of. Oh, okay.
Yeah.
And you're saying it's n to the C, to something C epsilon. C epsilon
yes.
is okay.
Yeah.
Oh, okay. And is it interesting to know what C epsilon is, or?
Yeah, we have. I mean, the form. I haven't put any details on. We can write this result. We have an explicit formula for.
Yeah. Okay.
And it's all well behaved. If epsilon is going to 0, you get. I mean, the right kind of behavior.
Okay.
I mean, it's just that I don't think those are revealing enough. I think just the structural part is fine. You can look at the paper to find out the details.
Sure.
So let me just give you very quickly as to how the proof gets carried out. What we really need to analyze is the L1 error that you're making. From the subspace spanned by the hub nodes. And here I'm going to take the top K high in degree nodes as my hub nodes. This is part of the proof as well. And that'll help in the algorithm too. What we'll show, if you look at this error, now I have a minimum over this. I'm not going to do the minimum. I'm actually going to give you a good candidate mu ks. These will be non-negative. They'll almost sum to 1. They'll asymptotically actually be summed to 1. And what I will say is that show a result of this, which is a lemma here, which says uniformly when I pick a node from V, this probability decays as n to the some C tilde epsilon for some other. And it's such that you can use the union bound thereafter to get the result. And how do you show this result? What we show, this particular error will only depend on neighborhood of S for a certain choice of mu S, the weights. And now what we then do is this neighborhood construction can then be compared with the neighborhood on the branching process. This is part of it, why we are studying it on the tree. And on this on the tree, this error actually is martingale-like. It's not exactly a martingale, it's martingale-like. And so you can use sort of bounded differences type methods to analyze the error. And this is where our concentration proof comes from. But this is sort of the steps. It takes a lot of work to get there, but nevertheless, that's what. Okay. So if I move along, what is the choice of weights, you would ask? So this is a beautiful result. So you can actually write one step of it down. The rest of it is quite interesting. It's not well known, which is kind of sad in a way, but that's fine. So if I take, say, if I look at pi wv, and I write one step of an iteration, right? So basically this is, if w was v, then basically in one step I'm reaching v again, I'm resetting. So I get this alpha term, all right, if w was v. Otherwise, I look at all nodes from v, I go to k, and then basically I get this 1 minus alpha times the number of nodes from where v goes to k, so the outgoing neighborhood of v. But then I throw in the personalized PageRank distribution corresponding to pi k. So this is sort of a relationship between different stationary distributions of different random, of different Markov chains on the same random graph, which they're all connected using the random walk on them. And then you can actually expand this further and write a particular relationship. If I give you this hub node K, you do modify the Markov chain, you run a different Markov process, and you can write this particular iteration that I have here. And one second. Yeah. So our edge weights are going to be the ones in sort of bluish purple. There are these something that you can calculate, pi tilde vk and alpha plus 1 minus alpha. And these are non-negative weights. We're going to choose this as the weights for our algorithm using what's called the hub theorem by J and Widom. So that was sort of tells you where all the pieces of the puzzle are coming from. I haven't told you what type of random graphs I have. And so we have to have two properties satisfied. The property one is kind of more, I think, our analysis problem. I think it's an artifact of that. We just need them to be sparse. So you only have a linear order n number of edges, okay, big O of n. And this is needed for the branching process approximation. There may be other ways to prove it. I don't know. But next one is what I think is more necessary. So we need the hub nodes, as I said. So basically, these are the high in-degree nodes. So when I add all the in-degree nodes of these nodes in the set K, I divide by the total number of degrees. As n goes to infinity, I should expect this to be finite. And this should happen for a sublinear number of nodes. So in some sense, I can think of my graphs conceptually as a bunch of stars, right? So a small number of stars and a large number of nodes hanging onto the stars. And we believe this assumption, the in-degree is vast, and I don't think there are that many nodes as google.com versus say, the number of people having web pages. And so the internet actually has this like a collection of stars type property, and that's why these algorithms work well in practice on this graph. So, I mean, one example, we did some tests here. So we look at power law degrees. Basically, power law, if you take that ratio that I was looking at, you take n to the 0.9 and to the 0.1 and let n go to infinity. It's sort of constant in a way. So this power law seems to behave, have this property. There is also, as I said, a geometric interpretation of this theorem. In fact, what our result is basically saying, for most nodes that are not in this hub set, I can approximate them well by these the specific weights that I said, mu v times pi k. And when the number of nodes is large, we also show that this basically, the non-negative weights almost sum to 1. They always are less than equal to 1. They asymptotically go to 1 as n goes to infinity. So effectively, you're sort of very close to a convex combination of the hub node. And this is the high dimensional picture that is emerging for this this problem is the following. Except you should take what the picture that I have with a grain of salt, because there is no way, it's not possible to get this to preserve distances when I project for this type of metric. All right, so let me skip this a little bit. So let me just go through the algorithm kind of fast, because I know I'm running a little late.
Yeah, we still have 5 more minutes, Vijay. I don't know.
Okay, that's good. Yeah, so I'll try to rush through that part. So give you a high level of what the algorithm is. So this idea of using hubs and then using them to estimate has actually been proposed in 2003 by Jay and Widom. Widom is actually, Jennifer Widom was the dean at Stanford now. And Jay, I guess once he proposed that, he went to a startup and he's made a lot of money on some ideas of this kind. All right. So what they do is exactly that. You find they say, I mean, choose a set of hub nodes. You estimate the PPRs directly for those hub nodes. For other nodes, use as a linear combination of the hub nodes. And actually, there's another algorithm by Pavel Berkin which is a follow-up to this one. It's called paint thinning, and that's a beautiful algorithm as well. And what they don't tell us is basically how many hub nodes to take. And I mean, they propose this, but there's no sort of analysis of the algorithm. There's no provable guarantees, and in some sense, we provide that. And what we show is that linear combination estimate is good for all but a little O of n non-hubs, if there are little O of n hubs. And what I'm going to do basically is rest of it is tell you how you can actually come up with an algorithm that will do this. So let me actually skip. Oh, this is an important part. All right, so the baseline scheme is basically I go out and estimate these pi k's, and then I estimate these weights, mu's, and then I say that, okay, if I know I can estimate your thing well, then I'm going to within the epsilon error, then I'm going to claim that my estimate is given by this summation. Otherwise, I'll go and seek the PPR again. Now this would, remember, I'm estimating pi's. So unless I can do online check whether this estimate is good or not, I will fail. It turns out in our case, you can, because of the structure of the problem, you can actually show that this estimate being good is the same thing as these estimated weights being bigger than some f epsilon. And this is some explicit function that you know. And what you can do is you can estimate the summation and is approximately in runtime, and so you can estimate the accuracy of the of what you're going to provide in runtime as well. Okay. I'll skip this one. Okay, this is important. So let's ignore the first part. Let's go to the bottom. I'm just skipping some things in terms of time. So the way we do it is the estimation is the following. We rely on the Anderson, Chung, Lang, and the Anderson et al. Algorithms. The Anderson, Chung, Lang is a forward dynamic programming. So what it does is start from a node, traverses important paths out of V. And it gives you sort of an L1 error guarantee for the values, that you get. And what it's actually doing is estimating the Vth row of pi. Okay. And this is what we'll use to estimate the PPR vectors directly. The backward algorithm, on the other hand, this is the Anderson algorithm. It basically, given a node, it traverses important paths into V. And this is going to estimate accurately a column of the Vth column of pi. And that they can do it in terms of infinity error, but you can also make it into an L1 error. And we are going to use that algorithm, actually a modified version of that on a modified graph. I don't have time to go into the details, to estimate the linear combination weights. Okay. So what I'm going to do is basically I will give you a candidate set of hub nodes, which will be the high in degree nodes. I pick some number of them. By forward DP, I will go and basically find all of their weights, PPR values. Then I'll use the backward DP to find the linear combination weights. If my linear combination weights are declared to be accurate, I will just use the forward DP and the linear combination weights to come up with the answer. If my estimator says, no, it's not, then I will go and ask again with the forward combination, go and get the PPR. And putting all of these together, this will actually tend to be accurate. And you can show under the our graph properties, this is the complexity is going to be the size of the hub set plus whatever you went out and asked again, times how much time it takes to estimate any of these vectors. And basically, since that is sublinear, this takes n log n, you get little O of n squared, and we can actually characterize an exponent there. I should just stop here, pause here, and say that I'm estimating an n by n matrix, and I'm running an algorithm that does little O of n squared. So I'm not even putting all the, I have lots of zeros when I estimate the matrix. I'm actually giving you a sparse matrix as opposed to a full matrix. I'm not even writing it down, because that will take me n squared time to do it. So I'm going to end and basically compare with the existing algorithms. So the best existing approach, I think there's a way to use the directed Laplacians. I don't understand that result well enough, but if whenever I do, I may get a sense of how that will work. And what you can do is basically run the forward or backward DP. I said the forward DP estimated rows, the backward DP estimated columns. I just do each of them independently. And so the error guarantee needs n log n. So I do this multiple times, I get n squared log n. Right? This is the type of complexity that you would get with those things. And the problem for this is basically it ignores structure and dependence across rows of the matrix. They're all running on the same graph. These are all Markov chains on the same graph. Where do you use it? And we use the structure very carefully because we characterize this dimensionality and then write on top of that. So the other way you could have gone about it, and I think there may be ways to modify this as well, is basically you estimate each element of this pi using the method of Lofgren, Banerjee, and Goel. And what they show is if you do work things right, to estimate one element, you take square root n log n. And so if you do every element, you're going to get n to the 2.5 log n. Again, the problem is it ignores dependencies across entries, and you should be able to use them. And that's what we say, how to use it to get reduced complexity. Finally, I'll end by saying, I said that what we're doing is a non-negative matrix factorization. I have an unknown pi. I split it up into non-negative factors n, k tilde n in little over n squared time. I think if you take the non-negative matrix factorization problem, it is hard in general, unless you have these, what they call hubs. Again, they use, but typically that literature assumes you know the matrix and then you do a factorization. Here I don't, in some sense, because of the structure of the problem and the matrix I'm estimating, I don't need to have the whole pi ahead of me, but I can just come up with a factorization. I think that's all I have in terms of time. Thank you.
Thanks, Vijay. So I don't know if there is, if anyone has questions, they can ask. If not, people watching on YouTube, they can comment or they can ask you directly or on the video.
Sure. Yeah.
Okay, I guess no questions. Thanks a lot, Vijay. This was very interesting.
Yeah.
Thank you very much.